Good morning, everybody. It is great to see how many of you have joined us here today, and welcome to this webinar, hosted today by Marc Auger, Business Development Manager of the Automotive, and Jean-Philippe Lavoie, Strategic Application Development Manager from Coherent. As a business development manager, Marc is focused on growing Coherent's automotive business by finding new and innovative solutions with lasers. Marc previously worked for a resistance projection welding company and Magna's body and chassis group. He started his career in production plants supporting stamping and assembly before moving to Metro Detroit, holding various positions in product design, sale, business development, and R&D. Marc has been working with lasers for over 20 years, having welded steel and aluminium for body and white in powertrain applications. JP earned his PhD in physics from Laval University in 2010. Following his doctorate, he held a product introduction engineer position at Coherent. In 2012, he joined Santa Carla Laser Applications Group as an applications engineer working on the development of the customer-based layer application. JP currently manages the Coherent North America Application Labs and oversees development for strategic laser applications, addressing the market demand for laser solution and challenging materials. We do encourage you to ask plenty of questions today. At any point during the webinar, please type in your questions into the Q&A box you will find at the bottom of the screen. At the end of the presentation, we will present your questions and answer as many as possible. It is a pleasure to have Marc and JP with us today, and I would like to warmly welcome them now to take control and begin the session.
Great. Thank you very much, Martin. Appreciate everyone attending and the We Automotive group for setting this up. Big thank you to those who have previously joined our webinar on battery welding, and looking forward to talking to you guys with regards to aluminum welding. So I'll start off with some basic overview of the company, and then JP will get into the details of some of the applications that we have. So I'll start off a bit with a quick introduction with regards to Coherent. So we are a US-based company with our headquarters located in Santa Clara. We're the second oldest commercial laser manufacturer, founded in '66. As you can see from the slide, sales of about 1.4 billion in FY19, just over 5,000 employees, and we have numerous manufacturing facilities located all around the world. For some of those of you who are experienced in high-powered welding, we did acquire the Rofen Sienar company in 2016. So, as I mentioned, we are a large global organization with sales and service located throughout the world with over 50 locations. We currently have inventory warehouses scattered throughout the world to provide spare parts as well as consumable support around the world, as well as 19 application centers located globally. Getting into a bit more detail with regards to these application centers, here in North America, where JP and I are both based, we have 3, we got 10 over in Europe, and 6 throughout Asia. We perform well over 2,500 applications annually for our customers with over 75 engineers. The goal of these applications is to provide support to the sales team to make sure that the correct equipment and processes are being selected, as well as helping out both pre-sales as well as after sales. Right, and this also is a location where we do prove out our latest and greatest technologies that we are bringing to the global customer base. Within Coherent, we can cover you all aspects of your needs for a laser. So there's the initial sale and support from the applications lab. We have extensive field service that will go out and help you during your install, setup and maintenance of your equipment, spare parts and logistics, technical support. So we're full industry 4.0 with capability for remote diagnosis, as well as extensive training classes, both at our facility or on-site at your facilities. There are 4 basic core markets that Coherent works in. There's the microelectronics, material processing, OEM components and instrumentation, and then government and scientific research. Right now, our largest market is the microelectronics. We are growing our material processing, and we are considered #1 in the market segment for the OEM components and the government research. What makes Coherent a bit unique compared to many of the other laser companies is not only the markets that we play in, but also our product offering. So here in this chart on the left, you can see that we offer all sorts of laser technologies, from gas lasers, diode lasers, solid state lasers, fiber lasers, and down to even full systems. So across the various core markets that we work in, we have multiple solutions. So when you come to Coherent, we can help make sure that the correct technology and process is being selected. And quite often, especially with new materials, there's more than one way of accomplishing this goal, but working closely with the customer, we can tailor the solution to meet all your requirements. And what's key here is process and application knowledge is critical. So that ties back into our applications lab, where we have the experience and knowledge that we can pass on to our customers. So with this broad portfolio that we offer, here's some examples. So down at the components levels, individual diodes, fiber delivery, switches. So we offer the individual components. We also offer sources and subsystems. So individual lasers, lasers with optic delivery that can be integrated into a larger line, as well as we do offer complete turnkey systems as well. So these images that you see here in the center is a label marker that's used for VIN label printing in the industry, tube cutters, precision cutters, high-powered welding systems. So we do have that capability of taking our individual laser components and subcomponents and delivering it as a complete turnkey system for you, the customer. One of the other big benefits that you have working with Coherent is our vertical integration. So here's an example of our fiber laser systems, all the way from growing the silicon wafers, the diode modules, all the way up through the finished fiber laser. So one of the things we like to jokingly say, we make every component except for the raw material, which in this case, you could look at it as sand. So this vertical integration allows us to optimize each stage of the manufacturing process to deliver the best possible product to you. Today, we're going to specifically be highlighting our latest advancement in fiber lasers, which is the adjustable ring mode fiber laser. So what's unique about this laser is the combination of two independent individual beams, one in the center or the core and one on the outer ring to create this. So what's unique about our systems is it is completely independent. So think of it as two individual lasers spliced into one. So you have the complete independence to control them individually. I'll get into some more detail and examples of that shortly. But in general, our standard lasers are available with power up to 10 kilowatts total. We can do larger by special request. And what's unique about our fiber lasers is we have closed loop power control. So what we say we're delivering is what we deliver. And we can do that all the way from 1%, so down in the hundreds of watts, all the way up to full power of 10 kilowatts. And we can change and manipulate that power level at a speed of up to 5 kilohertz. So we do not use any free space optics to combine these. So all the settings can easily and rapidly be changed just at the laser source. Our fiber lasers are also insensitive to backlight, as well as fully compatible with all the standard process optics and scanners out in the market today. As of today, we offer 4 different fiber sizes with the arm laser. And what we have is we have not only a detachable, but also switchable delivery system at our 100, 290. And then at our direct splice, we offer fiber sizes all the way down to a 22 micron core, which is using a single mode laser to pump that, as well as 50 and 70 micron cores. What makes the arm laser unique, and how will it improve your welding? So the key, there's basically 3 steps. You have the large outer ring, which preheats your material. So that helps shift the absorption, improves the efficiency of the coupling, right, which gives you less thermal gradient, so less thermal damage, as well as reducing your spatter. The high brightness, smaller center or core generates a very stable keyhole, providing uniformity in the depth and just overall process improvements. And then finally, that ring as well helps stabilize by maintaining the welt pool longer. So it gives you additional heat to reduce the cooling rate, which helps improve your process window. This is especially important with very crack sensitive materials such as 6 and 7000 series aluminum, which JP will be talking about in some more detail. Next, we have an animation showing how this independent ring core can help you in your weld applications. So what you see here is our laser. We're going to show exactly how the full independence works. So here's an animation where you can see, if you just want core power, you can adjust that on its own to effectively make like a donut weld. Ring. So here's your ring being controlled independently for that donut weld. Or you can vary them together, and you can also vary them at a different rate between each other. So they are, again, completely independent. And as mentioned, standard process heads and standard versions up to 10 kilowatts. Next, we're going to demonstrate an actual application on a vehicle. So this is an example of a remote weld, which is very common in the automotive industry. And you can see from the chart on the left, at the start, you can ramp them individually. Then you go into a steady state mode. And then a lot of the problems occur at the tail end of the weld. You can ramp them down individually to avoid issues in your weld termination. And in the end, you can eliminate the cracking, and you can have a significant reduction in spatter as well as pores. Where have we used this in production? So I'm proud to say that the new 2021 Hyundai Genesis G80 and GV80 aluminum doors are welded remotely with our arm fiber laser. We have applications as well in production doing aluminum powertrain components, battery components. We're welding titanium heat exchangers, stainless steel tube mills, as well as a lot of copper welding. Unfortunately, we're very limited what we can say in terms of actual OEMs due to NDAs, but rest assured that we also have applications coming in steel welding, high strength steel welding, as can be shown from this image. So now I'm going to be passing it on to JP, and he will be talking about specific applications with regards to aluminum materials that we've done in our labs for various different materials, sheets, extrusions, castings, and various configurations, as well as examples where we've collaborated with outside labs as well as key automotive suppliers for secondary validation of our technology. With that, I hand you over to JP Lavoie.
Thank you, Mark. Okay, so as Mark mentioned, we'll be talking about some of the applications in aluminum. So let's start first with the different challenges that we're seeing. So there's a lot of challenges welding aluminum. There's a high demand in welding 5 and 6,000 series, especially components on for the automotive. The OEMs are always asking for continuous welding if possible, as wire is great, but it does bring also some limitations sometimes in speed and complexity, as well as being able to eliminate hot cracking issues. The wire is usually used for that purpose, but we'll show you here some solutions that we have where we're able to eliminate the use of filler wire in a lot of cases. Other issues that we're seeing or challenges in aluminums is the porosities, and especially 5 and 6,000 series magnesium content being pretty high leads to a lot of cracking. We have lots of porosities, and we'll show you some solutions here that we have. Being able to control the weld shape and geometry is also very high on the list, especially thinking about fillet welds where it really matters, and we'll show you a few examples of that. And being able to increase the process speed and eliminating, if possible, complex equipment such as wobble heads is also an area of interest. So those are all the challenges that manufacturers are dealing with, and we'll show you some of the practical solutions we have to address them. So starting with an aluminum overlap here in the 6000 series. So this is a 1 millimeter aluminum overlap where top left of the screen, you are looking at a weld done 4 millimeters away from the end of a flange. And most OEMs would typically recommend being 6 to 8 millimeters away from the end of the flange. Problem being, if you look at the bottom left of that image, area where we used either a Gaussian or flat top fiber laser, so standard fiber laser available on the market, you see that the issue with the aluminum being that it conducts heat really well is that on one side of the flange, you have the material running and being heat sinked easily, but on the other side of the flange, the heat has nowhere to go. So you end up with a very high the temperature gradient right about to weld as the material cools. Additional stresses lead to the cracking, centerline cracking that you observe in the bottom left image. On the right side of the image, this is done with our arm fiber laser in an optimized beam profile. And you can see that weld 4 millimeters away from the end of the flange does not lead to any cracking. We've also been able to take it even closer than 4 millimeters from the edge without any cracking. What that does in return is that it can help OEMs and manufacturers design their flanges differently and save material essentially by not having to have such a long flange. Here's another example where we're looking at edge fillet weld in 6000 series aluminum again here, where we kept the speed at 5 meters a minute. That's constant. But the combined core and ring power has been adjusted from 2 to 3.5 kilowatts for these different welds that you're seeing. Also that here there is no wobbling involved, so this is a static beam just on the fillet weld. And why we changed the power, and what you can see here is that we're able to control the ring and core power to essentially shape the width and the penetration of the weld, which is a very nice advantage of the arm fiber laser to be able to shape the welds differently. Here's an example of a coach joint in 6000 aluminum. So this on the left side, you see the cross section of the joint. This was done with a filler material here. You can see, we can say also that this was successful without the filler material. However, when the material or the weld would go in a paint shop, this caused a problem because of the small radius left. So we have to use essentially a filler material to in order to limit the radius left so that paint can adhere properly to the part. What is interesting in the right side, you see the filler material being added, and you can see on some of the frames, you can clearly see the ring beam. You see the center core and the ring around it. I think you'll see it when the video reboots here. It will play one more time for you. There you go. So you can see at the beginning very clearly on some of the frames, the center beam and the ring around it. So that is quite interesting to see. There's some examples here in extrusions, 6,000 extrusions starting on the left side with a butt weld done with a filler material. In the center area is a butt weld again done with a remote weld. And then you have on the right side an overlap weld done again 6,000. If you look at the high-speed video, you also see that it is 6,000 series, and it is a pretty disturbed pool that you typically get on 5,000 and 6,000 series aluminum. However, you can see that there's actually not a ton of spatter being ejected out of the weld. The resulting weld at the bottom is what you see, the bottom image. And we were able in this case here to do a 5.7 millimeter deep weld in this overlap configuration, which is quite deep, and no cracking again, very little porosity. So very successful in extrusion materials as well. We've worked with all kinds of different casting materials. On the top left side, you see a butt joint done in sheet 2 casting. You're looking at about 2 millimeter penetration in this weld. And obviously, the shallower, the better in terms of limiting the porosities. The bottom left image shows you a butt joint done in casting 2 casting. This is almost 3 millimeter thickness. You see, obviously, a little bit more porosity, but in the weld, but nevertheless a successful weld. In the center area, you'll see in the top right, you'll see an overlap weld done from sheet to casting as well as casting to sheet. On the right side, top right, is that image is actually a 7 millimeter deep weld and from casting to into sheet, which is also again something pretty difficult to do with standard lasers. All of these were again achieved with the arm fiber laser by being able to tailor the beam shape and the parameters. All successful weld. Also done, as you can see, on an edge fillet and a casting to casting in overlap configuration. Now, you don't have really to take our word for it. You can look at some of the presentations and papers published out there. A lot of our partners have tested the arm fiber laser and shared some results with us. So there's some of the collaborations that we have. Just to show you, is a study done here by KUKA at their development center here in Sterling Heights, Michigan, where they used a 1.3 millimeter top sheet 5,000 series aluminum, and they welded it on an overlap configuration to a 1.5 millimeter bottom sheet 6,000 series aluminum. This was done with a HIAG RLSK remote head, and they kept their travel speed at 4.5 meters a minute. This is linear travel weld with no oscillation, we should mention. What they observed is that on the left side here is what you typically see with a standard fiber laser sold on the market. You'll have either a top hat or Gaussian mode fiber laser on the left side. Out of a 200 micron fiber, you see there's a lot of micro cracking on surface visible. On the right side is done with the arm fiber laser with an optimized ring to center ratio. You see here they used a ratio ring to center power of 1.55. which turned out to be their magical ratio here for this specific configuration, and you see no cracking. Beautiful weld. Now looking at the longitudinal cross-section of these two welds, you see on the left side standard fiber laser shows a lot of porosities, especially near the bottom of the weld and the root where you'd expect to see it. And on the right side, very little porosities for the arm fiber laser weld. Looking at the microstructure of these welds in the transition zone going from the weld into the parent material, you can see on the left side again the regular fiber laser showing a lot of micro cracks, whereas you can see the smooth transition on the right side with the arm fiber laser, and no micro cracking is visible. Then this shows you also the similar study that we did where they were doing a flange reduction study. On the left image shows you standard fiber laser with a 6 millimeter away from the edge of the flange. See that again, the heat builds up on the the end of the flange, and you see micro cracks and cracks all over the place. On the right side, they did the study 4 millimeters away from the edge of the flange, from the center of the weld to the edge of the flange, and you see no cracking again. So they confirmed the same results that we had done in our lab. Here's another study here done by ScanSonic in Germany at their application center, where they use an 8 kilowatt arm fiber laser and their RLWA head with a 2.9x magnification. Should mention here that this process head, as well as virtually all of the commercially available head, you'll take Precitec, you'll take the RLSK heads, have now dual control integrated so that they're fully compatible with our arm fiber laser series, where we can control the center core and the ring independently. So all these heads and their software is compatible with our system. So in this case here, they use their head and our laser to do a gap bridging study in aluminum. What they found out is that, as you see on the left side here, is they added a 700 micron gap in the center of a part where they were doing a fillet weld. And they also did the same, adding the gap on the right side, in this case, of the weld. And as you can see, the process head was able to essentially adjust the laser parameters and the optical parameters to be able to bridge that gap successfully. Now, this is very interesting in that you're looking at the same fillet weld, but here no clamps applied. So the material essentially is just laid on top of each other like this, and you can visibly see that there's a huge gap in the center. And what's interesting is when the laser is turned on, it is automatically being adjusted, and you can see that this part essentially is warping and moving, but the beam and the laser parameters are automatically adjusted to get a successful weld. So very interesting. Next is at Gestamp, the R&D center in Michigan as well did some work with a Precitec weld master head. They had a pretty interesting setup in the center image there. You see the Precitec head with all kinds of different sensors and options. And on the right side was mounted on the KUKA robot. They use essentially this head, which is again compatible with the arm fiber laser for both center and ring beam control, to do a door welding application where they were welding 6,000 series outer skins to 5,000 series. You see on the left side the image of their setup, and on the right side the red line essentially shows you the seam that is being tracked and welded. Again, this is done with it's a good replacement for tactile welding. This is done remotely with wobble is being applied. However, if you look at the detail of the study, it shows that the speed achieved is more than 6 meters a minute, which is quite interesting results. So successful application done with the arm laser in this head. Here's another one where they use an aluminum extrusion for battery tray application. You have a 3 millimeter thick extrusion part in green on the left side in the image there, welded to a 2 millimeter thick 6000 series stamping part. And you can see on the right side the results. They did both a continuous remote weld as well as a stitch weld on the bottom area there. And the bottom right image shows you the resulting fillet weld that they achieved, which was again very successful, done with the arm fiber laser. The Gestamp took it even further, where they looked at all kinds of different material combinations, whether it is 5 to 5,000 series aluminum. This is your top image, to the center image, which shows a 7,000 series aluminum welded to a 6,000 series in fillet configuration, and then the bottom 7,000 series welded to 5,000 series. Can definitely see that the center and the bottom welds are definitely a little bit rougher than the top, which you would expect for 7,000 series. but that is an interesting result that they're able to successfully weld 7000 series to other series, even in 2 mm thickness, which is also pretty thick. With this, I will stop here and would like to thank you for your attention, and we are more than happy to answer any questions you might have.
Mark, JP, thank you very much for that. I'm going to dive into some of the questions. So here we go. The first question is, have your ARM fiber lasers been implemented to a global customer base?
So, as I mentioned earlier, unfortunately, we can't give you a lot of the details of what customers, but yes, we have numerous ARM lasers out in the field, installed globally for numerous applications. The one specifically I can reference is the 2021 Genesis from Hyundai, the G80 and GV80 aluminum doors. But yes, we have numerous installations globally.
Thank you. Next question. What are the main benefits of ARM laser fibers over standard fiber lasers?
Yeah, I can answer that one. It's a great question. We covered a little bit of that, obviously, maybe a little quickly at the beginning, but essentially, it really is a different type of laser system. It does wear the name of fiber laser, but having the ring and core and being able to control independently the ring and the core gives you really a new perspective or it's a new knob to turn in the lab when welding challenging materials. And what we see is that in a lot of these challenging materials, in this case here, aluminum, the ring really helps by being able to preheat and post-heat the material and really control the in a lot of ways the heat, the cooling rate essentially of your material. Aluminum is very sensitive to high temperature gradients, and the ARM fiber laser really offers a way to calm down this temperature gradient and get around a lot of the cracking issues that would result from it, as well as the ring offers additional benefits in that it offers a wider and more stable keyhole. A lot of the problems with porosities in this case is that when the keyhole collapses, is that you have trapped, air bubbles and contaminants in your part. By having the keyhole wide open and then not collapsing, you're not only able to vent and allow all of this gas to escape your keyhole, but by having it not collapse as well, you're avoiding a lot of the porosities that get trapped in the part. So it really is a multifold benefit that you see from this laser. So I hope that covers anyway some of the benefits on the aluminum parts.
Thank you, JP. Next question. For an OEM, is there a big cost differential between ARM fiber lasers or standard fiber lasers?
Sure. So, due to the way that the laser is configured, unfortunately, it's not necessarily a direct comparison. So you can't just say, oh, well, I'm using a 6 kilowatt standard fiber today, so give me a 6 kilowatt arm. So one of the things that you have to take that extra step to look at it, because quite often the total power is different. So it's difficult to do it as a direct replacement. What I would say is that there is an increase due to some added complexity within the laser, but quite often there's ancillary benefits. So for example, quite often we can eliminate the need for an oscillation optic. So if you can go from a wobbling optic to a standard optic, the increase in the purchase price of the laser can be more than offset by a decrease in costs of optics. Quite often, speed is significantly improved. So it really takes a full analysis to make sure, and in most cases we're actually showing an overall cost savings, even though the purchase price of the laser by itself may be slightly higher than a standard fiber.
Okay, thank you, Mark. Next question from Jack. Could you please confirm what casting alloy and process was used, please?
So multiple alloys. So we've looked at varying grades of high pressure vacuum die cast alloys that are being used in structural applications. So your Oral family. We've also looked at more die cast components for both powertrain as well as, if you want to call it, non-structural. So, you know, A380 type alloys, but the number and types of alloys are numerous, right? So we're not limited to just one particular family. So I would encourage Jack to reach out to us with his alloys of interest, and then we can let him specifically know if we've already looked at it or not.
Okay, well, it's another question from Jack, actually, Mark.
Sure.
Could you confirm the alloys welded on the casting slides? Are there any limitations of welding castings to extrusions that you observed?
So what I would say is with castings, it's very dependent on the incoming quality of the castings, right? So depending on the area of the casting, you know, the quality of a casting is not necessarily consistent throughout it. So you have to, in order to implement it successfully in production, you got to work closely with the casting supplier to process the part to minimize the level of porosity in the areas to be welded. So there's not necessarily a clean answer. You know, with some customers, they mandate that there is some machining that has to be done in the area to be welded to help control the quality of the casting. So we can't inherently change the property of the casting, right? With the wider process window, we can definitely improve your results. But what I would say is the arm is not an excuse to avoid the need to have a properly designed and produced casting.
Thank you, Mark. Next question. What are the most important recent developments in beam technology?
I suppose I can answer this. The most recent development beam technology. I mean, I would say that the arm fiber laser really is the greatest investors that we have in terms of beam technology and in being able to address challenging materials. It really offers all kinds of different beam shapes that are available, from, you know, pure center beam that is more Gaussian going to a pure donut or anything in between. So that offers, you know, quite a bit of flexibility. I hope this addresses this this question. If not, I do encourage whoever asked the question to reach out to us, and we'll be more than happy to elaborate a little bit more.
Thank you, JP. Before the next question, somebody's just written, Hyundai, great example of an OEM client. Appreciate, not always possible, so thank you. The next question, I understand ARM improves weld quality. Does it also improve weld time for a manufacturer?
Well, this touches a little bit into or ties in what Mark was saying. So in a way, of a lot of benefits in that, as Mark mentioned, a lot of cases we're able to eliminate wobble. And then if you go with a static beam, you can typically travel significantly faster. We've also observed that in a lot of cases, since the ring on aluminum, since the ring really preheats and postheat the part, the center beam that creates the keyhole does not need nearly as much energy to create the same penetration weld. So then the customer is presented with options to either travel faster, or you can essentially reduce your laser power to keep the process the same speed that you had with a standard fiber laser. Reducing the power allows you to maybe buy a smaller laser. That can be additional benefit. So yes, there's definitely some, I think, advantages in multiple different ways over standard technology.
Okay, thanks, JP. Next question. Many thanks for a great presentation. Could you please explain if ARM is able to deal with aluminium oxide layer before welding?
This is also a very interesting question. Yeah, so we have done so much aluminum welding over the last few years on different series, and yes, the short answer is yes, it can address the oxide layer in that. Having a more stable and wide open keyhole really helps get rid of a lot of the impurities, and we're seeing definitely additional benefits. We've had materials that would come in and were, let's say fresh, where oxide did not have time ready to form, or they were cleaned and processed immediately. And we've also welded parts where material was sitting on shelf for 6 months, where you're guaranteed to have a pretty thick layer of oxide. We were able in all cases to weld. Now, will the material that has been freshly cleaned with no oxide look better at the structural level in smaller porosities and fewer porosities? The answer is yes. Is the material that has been sitting around for a long time not viable for production application? I do not think so. In a lot of cases, in all cases, we're typically able to weld these materials successfully and send them back to the customer for evaluation. And I haven't heard that these materials are not passing their requirements.
And to build on JP's answer, it really comes down to the customer's quality requirements, right? What I can tell you is, they're typically the European requirements from the OEMs over there are much stricter when it comes to the weld quality and their expectations on what the weld quality is compared to a higher volume manufacturer here in North America, right? But typically, the cost, the material, the cleanliness of the incoming product. So that there are ways to manage it. It just comes down to, what you need from your requirements from the end customer. So, if you're willing to trade off, as JP said, some wider variation because of the varying oxide layers, then it's doable. So it really comes down to the individual customer.
Thank you for that. Next question, please. Can you give some more examples of advancements in joining methods?
So when you start talking about laser, right, you have, as we mentioned, quite often you can use fixed optics. One of the interesting technologies that was presented and actually implemented for the Gestamp study is the Master system allows you to synchronize power modulation to the oscillation. So as the beam is weaving back and forth across the weld, not only are you weaving it to move it, you're actually changing the power independently between the ring and core during that weave. So a lot of it is not necessarily specific about the laser itself, but it's how you implement it with the optics. Within Coherent, we do have an optic system called Smart Weld Plus, which allows you to do very intricate 2D patterns in combination with power modulation. For the thicker materials in body in white and powertrain, we don't see the need to do that as much. There is benefits, but when it starts coming to the microelectronics and battery connections, so in the last webinar that we did, and I encourage you to look at it on WE's website for the battery welding, we had lots of examples where we were welding dissimilar materials and very sensitive materials, copper, aluminum, where being able to do unique patterns as well as modulating the power within that pattern can really let you do some amazing things.
Thank you very much for that, Mark. Next question. Can Coherent customize the ARM fiber laser in advance of installation based on intended use, or is it one size fits all product anyway?
So great question. So as we showed, currently we offer 4 different fiber ring core diameter sizes that are released and available for delivery. So one of the reasons that we had to do that is also with regards to optics and applications. So, you know, the sales team and our application team would be more than happy to work with you to understand what your needs are, to be able to help select the correct combination that's needed for your process. So not only fiber core sizes, but also power sizes, you know, with the ability to customize how much power in the ring and how much power in the core independently, that, you know, we can do a lot of upfront work in our lab to show you, you know, what the benefits are depending on what you're looking for, right? So if you have a preferred optic supplier, you know, that magnification, we can work with you. So that's all done upfront.
Thank you very much for that. Next question. With laser welding of aluminium, can you say more about the use of shielding gas and or compressed air to blow away plasma smoke? Is it necessary when ARM is used?
Very, very interesting question. Actually, this is we didn't cover this, and I'm glad somebody asked. Yeah, so both can be done. We started initially when the ARM laser first came out. We started, welding aluminum. We used a lot of shield gas. Because that's what we were used to a lot, and in welding. And then more and more requests came to use compressed air and or just use nothing at all. What we are seeing is that using nothing at all does not really work all that well, in that you still have a plume that is formed, and this will obviously impact your being focusing into the part. But what we found works well for OEMs, and what is done a lot is that people tend to use fans that are typically a few meters away or a few feet away from the part. Blowing air across the part is sufficient, essentially, in almost all cases, to weld successfully these parts. It just blows the smoke a little bit away out of the way of the laser beam, and that is sufficient in being able to achieve a good weld. That said, if you were to use shield gas, obviously it provides very good quality welds as well. Is it needed? Again, depends on the application and the customer's requirements. We find that in a lot of cases we can do away without.
Perfect. Thank you very much. Next question. Is the surface able to be e-coated post-welding? And is there a noticeable difference in adhesion of this e-coat layer?
So when you're e-coating a part, surface roughness and oxides on your surface play a big role in the adhesion. So depending on the configuration and depending on the materials, there has been a noticeable improvement in the surface roughness using the ARM laser. So again, it'll come down to the initial combination, the combination that specific combination that you're using, but there has been quite a bit of work done both by ourselves as well as our outside partners to show a improvement in the surface roughness of the part. So as JP has mentioned, we have a much more stable keyhole. We have a lot less spatter, a lot less porosity. All that results into a smoother surface. I'm sure, as the person who asked the question, there are instances in production today where a secondary pass after the welding is required with standard fiber lasers to, remelt / smooth down the surface. There's multi-spot solutions where you have a trailing spot after the fact to do it. So is there a chance? Yes. But the individual combination would have to be tested and validated. But in general, we do see a big improvement in the surface roughness, which should help with that situation.
Thank you, guys. Next question. What are the benefits of laser welding comparing to mechanical joining for joining aluminium parts or dissimilar material stack-ups?
Really good question. So in general, for an aluminum to aluminum welding, there's a few key benefits. So one, most mechanical joining processes such as clinching, self-pierce riveting, bolted joint require two-sided access. So with a laser, you're able to do single-sided access and avoid the need to have large cutouts or access holes to get in. So think of it, if you're welding a sheet to an extrusion where you have a closed structure, from a mechanical standpoint, that forces you into a single-sided access such as a flow drill screw versus a clinch or self-pierce rivet. The other big benefit going along with that will come down to clamping and fixturing, right? If with a lot of these mechanical processes, you have very high forces required. So with the laser, you can get away with different clamping technologies. You don't need the support to resist the force. The two major benefits that typically OEMs use are the speed. So especially if you're using a remote head, you're traveling, let's just say the weld at 6 meters a minute, but when you have to jump between, instead of having to have the robot move a tool to get around, to get new, all you have to do is move a mirror. So your time to weld is significantly reduced, which can eliminate the number of stations, your overall footprint, your floor space. Additionally, if your mechanical fastener is a self-pierce rivet or a bolt or a flow drill screw, you have the additional weight and cost of that consumable that you're putting as part of the process, right? Now, quite often a mechanical joint from an overall strength, because you are not melting and affecting the material properties, there can be a trade-off in joint strength, but quite often, 2 or 3 welds can be done in a fraction of the time of one mechanical fastener to make up any of the strength disadvantages. Just like eliminating filler wire, any metallurgist that's listening, as you heat it up, you're going to vaporize some of the alloying elements, and you can get higher strength with the filler wire, but the increase of speed and the reduction in cost, quite often with some product design changes, you can accommodate that to gain the cost savings. With regards to the question of dissimilar materials, any fusion process with regards to dissimilar materials will have some challenges and drawbacks, right? So you see very minimal the use of, especially in structural applications, lasers to weld dissimilar materials. There's ways of brazing so that you're not actually melting the residual or the parent materials, causing intermetallics and both weaknesses from a structural standpoint, as well as worrying about dissimilar material corrosion. So dissimilar joining with lasers is a much bigger topic that could be multiple webinars on its own, but hopefully that gave enough of an answer.
Thank you, guys. Next question. How recent is this technology? Impressive.
Right. This laser has been released about, we're going on 5 years, I believe now with this, and obviously first came out with one version, which was the 70 micron core diameter, 180 micron ring diameter. Over the years, more flavors of the laser was added to our portfolio to essentially address new challenges. So we're talking about the growing interest in e-mobility, for example, where we have now a very high brightness option, arm laser with a 22 micron center beam and 140 or 200 micron ring diameter. And so, yeah, there's definitely more options. We have the option of a standard laser with a disconnectable fiber, replaceable fiber, delivery fiber. That is a new option that came over the years as well. So there's definitely a lot of different flavors out there available to address just about any applications. We're constantly looking at our customer applications and monitor what comes in. And we keep working with our customers and internally to develop new lasers, essentially new different flavors to address these challenging materials that are presented to us.
And just to build on what JP said, is the laser was developed over around 5 years ago. The largest, the main commercial applications where customers were using in production really started about 3 years ago. And over the last 2 years, the growth of the arm laser, it went from, 1 or 2 units to try it out on troublesome parts to multiple unit orders across multiple facilities globally. So, it has really taken off. And as JP mentioned, especially with the recent offerings of the different fiber sizes, we've seen huge growth in the e-mobility market, just like the rest of the industry. And this has really been a very good product for Coherent.
Thank you for that. Next question. Are there any further application examples you didn't mention?
Oh, there's there's a lot. Again, we could talk. This is why we broke this presentation into multiple different webinars. We had one on e-mobility, for example. So there's a lot of applications in that we're seeing in obviously joining aluminum and copper being demanded in e-mobility, whether it is bus bars and foils and hairpins, for example. There's a ton of applications in advanced steels. You're looking at all the high strength steels out there with very high strength. The aluminum alloys, those are really the areas where we see this technology being demanded and we're exploring. And again, the number of applications just keeps on growing for these types of materials. So we try to apply this technology where we see fit, where we see that other technologies that we have are limited and it would apply, then we go and try it. One other interesting application that also we explored is the in powertrain components welding. This used to be very much a CO2 high power CO2 world due to the high demand for the shape of the weld as well as the very low spatter that's demanded for these applications. And we have been able to demonstrate that our arm fiber laser with proper beam parameters selection can weld and do as well as a CO2 weld is a direct replacement. So that is very interesting, as it was an area that had been untouched for years, as CO2 was rated gold standard. But now the arm fiber laser offers really good comparable results for these welds.
Thank you very much. Final question. What are some typical laser spot sizes of the core and ring that you use for the examples given?
Yeah, so this again could go on for quite a while. I'll just try to summarize it a little bit in buckets. We find that for materials like aluminum, high power aluminum, what we talked about today, We find in a lot of cases that the 70 micron core and 180 micron ring, for example, is a good laser for a lot of these applications in that it offers very high power density and is able to melt these materials very efficiently. Talking about high strength steels, for example, again, the 7180 being a good choice. However, we're seeing that the 100 micron 290 ring fiber laser is also a very good choice, as quite often larger diameter spot sizes are required for these. So this laser tends to perform well in these types of applications. In e-mobility, for example, the 70 micron core can be a good choice as well, with very high brightness 22 micron core arm laser. We're seeing also that a lot of applications out there, and a lot of talk about different wavelengths. The arm laser not only applies to the IR wavelength, but we're seeing that we're able to quite often do better or equal or better than other wavelengths. Some of our competition out there is promoting quite often wavelengths like blue and green. We're asked quite often about blue and green wavelengths, especially for copper welding and aluminum. And we have found in the lab that the different parameters that we're able to play with on the arm fiber lasers are able to generate as good, very equal welds, or even actually exceed welds that are done with green and blue in a lot of cases, and that we're able to go deeper and faster. So we're not initially seeing that it makes a whole lot of sense to go to these other more expensive wavelengths. Just to keep in mind again that a blue or green photon will typically cost you almost 8 to 10 times more than an IR photon. So there's definitely something to discuss here with customers when it comes to laser selection. So we do encourage all of you on the call and the ones that participated today to reach out to us if you have any questions, whether it is on wavelength or for your specific materials. We'd be more than happy to discuss with you your applications and provide the solutions that we tell you about, the solutions we have to offer.
JP, thank you very much for that. Mark, JP, I just want to finish with what somebody's just written. Thanks, Mark and JP. I'm new in my job role, and this was very useful webinar for them. So you've done some good today.
Thank you.
Thank you everyone for your time and listening. And if you want to learn a bit more about what you can do with steel, I encourage them to listen to the conference in 2 days at the same time.
Exactly. I'll just close up. Ladies and gentlemen, I would like to say a big thank you to Mark and JP from Coherent for an excellent presentation today. The webinar today will be on demand for you to rewatch as well. Thank you to everyone who has registered and attended this webinar. And once again, many thanks to Mark and JP for an excellent presentation. We look forward to seeing you all at our next We Automotive webinar. And the Coherent one is again on this Thursday, the 30th of July at, again, 11 a.m. ET time and 4 p.m. GMT time. So once again, Mark, JP, thank you very much and goodbye.
Thank you, Martin. Enjoy.
Thank you.